Welcome to this video where we take a look at chapters 22 to 25 of the first edition of Whitehead and Russell's Principia Mathematica. This video will complete the contents of section C, Classes and Relations, the first two chapters of which I looked at in a previous video. Since I've already looked in detail at the concepts of class and relation as they appear in Principia Mathematica in a previous video, then I won't repeat them here. I will assume in this video everything that I've covered in my previous few videos covering the chapters from 1 to 21, and I'll only revisit that material when it's necessary to do so in order to better explain something in the present video. I'll cover the contents of these chapters in a different order to which they appear in Principia Mathematica, and so I'll be going through the chapters in the following order: chapter 22, 24, 23 and chapter 25. In fact, most of this video will be dedicated to the contents of chapters 22 and 24, which are titled Calculus of Classes and The Existence of Classes, respectively. The other two chapters have the similar titles, Calculus of Relations and The Existence of Relations, respectively. As you'll see for yourselves, if you look through a copy of Principia Mathematica, chapters 23 and 25 are essentially just two lists of definitions and propositions. No demonstrations are provided at all. And this is because the proofs of the propositions are completely analogous to the proofs in the corresponding chapters relating to classes, so I won't actually be saying anything substantial in this video about these two chapters in reality. I expect this video to be shorter than some of the previous videos that I've made on Principia Mathematica, and I won't be focusing so much on demonstrations in this video. As I've mentioned in the previous video, I've said about as much as I really need to say about the style of demonstrations in Principia Mathematica, and other than a few minor points here and there, I typically won't be going into too much detail, although there is one demonstration that I have a few things to comment on. So let's have a look at chapter 22, the Calculus of Classes. In this section, we see many of the, what would nowadays be considered usual properties of classes or sets being demonstrated. The important definitions of this chapter are shown on the screen now. 22.01 defines the inclusion relation between two classes. 22.02 defines the logical product of two classes. 22.03 defines the logical sum of two classes. 22.04 defines the negation of a class, and 22.05 defines subtraction of classes. Note that we don't require beta to be completely included in alpha. As an extreme, if the class beta has no member in common with alpha, then alpha minus beta is simply equal to alpha. And there are another two definitions to give later in this chapter, but they're really just notational shorthand definitions, which I'll give later in the video. It will probably be noticed quite quickly that the logical sum and logical product of two classes as defined in Principia Mathematica are conceptually similar to the union and intersection of two sets in modern set theory. However, in this video and any further videos that I make on Principia Mathematica, I will continue to use the terms logical sum and logical product when referring to the classes of Principia Mathematica, rather than using the set theoretic terms union and intersection. And I do this to make a clear distinction between the classes of Principia Mathematica and the sets of modern set theory. I'll also try to use the term member when referring to the classes of Principia Mathematica rather than element. Having said that, if you already have some familiarity with elementary set theory, then you will probably find much of sections 22 and 24 very predictable. Chapter 22 really doesn't contain any surprises for someone already familiar with modern elementary set theory. Not knowing about how classes work specifically in Principia Mathematica wouldn't really prevent you from recognizing and understanding reasonably well the contents of chapter 22. Nevertheless, as previously mentioned, to even get close to understanding Principia Mathematica as it is, we need to approach the contents of these sections from Whitehead and Russell's perspective and using the system of Principia Mathematica. And this will lead to some important distinctions between the kinds of things called classes in Principia Mathematica and the kinds of things called classes or sets elsewhere. And it's to avoid conflating these two concepts that I will try to avoid using language which I think has a kind of set theoretic vibe to it. Something that will seem very obvious from a modern perspective is that class inclusion is not the same as membership of a class. This wasn't always clear in the early development of class or set theory, and we see from proposition 22.44 that class inclusion is a transitive relation between classes. However, as we might expect, membership in a class is not a transitive relation. 22.441 and 22.46 give an idea of how the concepts of class inclusion and membership relate to each other. The set of postulates stated on page 218 is a set of postulates suggested by Huntington, which could be taken as a possible set of postulates which would give rise to the algebra of logic. Note that Whitehead and Russell use different notation on page 218 of Principia Mathematica than the notation which is used by Huntington in the quoted article. I've not read Huntington's article in detail, I've only really skim-read it, so I can't really give any detailed comments on it. However, in the referenced article, from what I can see, Huntington suggests 3 separate possible sets of postulates which could be taken as a basis for the algebra of logic. He proves the consistency of each set of postulates and the independence of each postulate from all of the others in the same set. The first set of postulates concerns the relations in Principia Mathematica called logical product and logical sum, and the entities which in Principia Mathematica are called the universal class and the Null-Class, and their basic properties. These 2 classes will be defined in chapter 24, which I cover later in the video. The second set of postulates concerns the relation class inclusion and its basic properties. And the third set of postulates concerns the basic properties of the relation logical sum and the classes the Null-Class and the universal class. In Huntington's article we read, having chosen a set of fundamental concepts and a set of fundamental propositions for each of the 3 sections, I show first that the fundamental propositions of each set are consistent and independent, and secondly that the fundamental concepts of each section can be deduced from the fundamental propositions of each of the other sections. Then we may say first that each section determines a definite algebra, and secondly that the 3 algebras are equivalent. Finally, in order to justify the name algebra of logic for the algebra thus established, I show that the fundamental theorems of that algebra, as set forth in standard treatises like those of Schroeder and Whitehead, can be derived from either of my 3 sections. Thus we see that Whitehead and Russell will go on in sections 22 and 24 to prove that each of Huntington's postulates holds in the system of Principia Mathematica. We read on page 218, assuming Huntington's analysis of the postulates for the formal algebra of logic, the propositions proved in what follows suffice to establish that this algebra holds for classes. Thus, once all of Huntington's postulates are proved, then Whitehead and Russell are satisfied that the classes of Principia Mathematica behave in precisely the way that we would like them to behave. The formal similarities between some of the propositions of this section relating to classes and propositions demonstrated in previous sections relating to propositions are noticeable. For example, compare propositions 22.42 and 2.08, 22.43 and 3.26, and 22.47 and 3.41 to give a few examples. Other propositions concerning classes which are analogous to certain propositions concerning propositions are given as examples on page 29 of the introduction. And these similarities are entirely expected since they are a direct consequence of the definitions 22.01, 02, 03, etc. For example, the expression alpha is included in beta is, by definition 22.01, seen to really be a proposition of the form P implies Q. The expression X is a member of the logical product of the classes alpha and beta is seen to be, by definition 22.02 and 20.3, really a proposition of the form P and Q, and so on. And indeed, on page 28 of the introduction we see both classes and relations have properties analogous to most of those of propositions that result from negation and the logical sum. The authors go on further to say, the logical product of 2 classes, alpha and beta, is their common part, i.e., the class of terms which are members of both. And the logical sum of 2 classes, alpha and beta, is the class of terms which are members of either. The definition is, the logical sum of alpha and beta is the class determined by the propositional function x is a member of alpha or x is a member of beta. And the connection with the logical sum of propositions is given by the assertion as shown on the screen now. It's worth noticing that in some of the propositions towards the end of this section, the demonstrations of the propositions are omitted, and in some cases a single proposition is referenced should the reader want to reconstruct the demonstrations themselves. It will be immediately noticed in some cases, for example, proposition 22.83, the formal similarity between proposition 22.83 and the referenced proposition 4.11. Thus we see the close relationship between the propositional calculus and the calculus of classes. Of course, the two are not identical. There are some differences between the two. That is, there are some propositions relating to classes which have no propositional equivalent. So I'll just pick out some of the more interesting propositions from this section. I won't be mentioning every proposition. Most of them are fairly self-explanatory, and as I've already mentioned, will be easily recognizable to anyone who has even a rudimentary knowledge of elementary set theory. And the truth of many of the propositions can often be seen by considering Venn diagrams, for example. Of course, Venn diagrams don't equal rigorous proof, but they can be useful to at least convince yourself. So 22.36 and 22.37 show that the logical sum and logical product of classes gives a new class, and 22.38 shows that the negation of a class is again a class. Of course, for the logical sum and product of two classes to be significant, the classes must be of the same type, and this follows from, say, propositions 22.33 and 22.34. In proposition 22.33, we see x appear as a real variable, and so the x that is to be an object of each of the classes alpha, beta, and the logical product of alpha and beta is the same object in each case, and so is of a particular type. Recall that the type of a class is determined by the type of the objects which are its members, and the members of a class must all be of a single type. Therefore, if alpha and beta were of different types, then their members must be of different types. And since an object x cannot be of more than one type, then x could not simultaneously be a member of alpha and beta. Similarly for 22.34, and remember that significant does not mean the same thing as true. The negation of a class alpha is another class whose members are all of those objects which are not members of the class alpha, but nevertheless which are of the same type as the objects which are members of alpha. And by 22.351, a class and its negation are not equal. Thus, a class and its negation are classes of the same type. If alpha has its members all objects of a certain type, then its negation, as we'll see in chapter 24, will be the null-class. Propositions 22.39 and 391 show respectively that the class that is the logical sum, respectively logical product, of two classes, which are determined by the functions phi and psi, is determined by the logical sum, respectively logical product, of the functions phi and psi. 22.392 shows that the negation of a class determined by the function phi is itself determined by the negation of the function, that is, by the function not phi. I informally mentioned this in the previous video, but here it's made official. 22.44 shows that the relation of class inclusion is a transitive relation. 22.52 shows that the logical product is associative, and hence we have definition 22.53. And we similarly have 22.7, which shows that the logical sum is associative, and hence we also have definition 22.71. Propositions 22.68 and 22.69 show how each of the operations logical products and logical sum distribute over one another. And there's a couple of typographical errors on page 224 in propositions 22.84 and 22.85. The right-hand sides of each equality should be a logical sum of classes symbol, not a logical sum of propositions symbol. Of course, the logical sum of propositions, the or symbol, is meaningless when applied to classes. And these two propositions, 22.84 and 85, as well as 22.86 and 87, are De Morgan's laws. 22.88, every object of a certain type must be a member of the logical sum of a class and its negation. And 22.89, no objects of a given type can be a member of the logical product of a class and its negation. In this chapter and henceforth, it will be very usual to see the class symbols alpha, beta, and so on, rather than the x hat phi x notation for classes. And this indicates that, generally speaking, we don't really need to worry too much about which propositional function determines the class. And this is very convenient, since to use the notation x hat phi x, or even to try and replace all the propositions involving class symbols with their definitions according to 20.01, would quickly become unmanageable. It's always, in theory, possible to completely eliminate class symbols of any kind, but in practice, not a good idea. I'd recommend that you try it for yourself, take a proposition that's proved in Principia Mathematica with class symbols, and try to eliminate all of the class symbols and see what kinds of monstrosities you obtain. As we saw towards the end of section 20, namely propositions 20.6 onwards, showed that class symbols as apparent variables can be directly manipulated using the propositions from chapters 10, chapter 11, and so on, without replacing them with their definitions in terms of propositional functions first. And we see in the demonstration of proposition 22.94 how the propositions cited, 10.1, 10.11, and so on, are being applied directly to the expressions involving class symbols. And this is, of course, a consequence of the proposition proved towards the end of chapter 20 from 20.6 onwards, and which I spoke about in the video which I made covering the contents of that chapter. The line labelled 1 in the demonstration may seem quite confusing at first because of how the class symbol alpha is being used, and I'll explain what I mean. We see on the first line of the demonstration as shown. In the antecedent of this implication, alpha is an apparent variable. In the consequent, the alpha that we see is not the same as the alpha in the antecedent. The alpha in the consequent is a real variable and represents any. This proposition could be replaced with any of those shown on the screen now, as merely a few examples, without changing the meaning in any way whatsoever. Now, just before moving on, it's interesting, for me at least, to note that Whitehead and Russell cite proposition 10.1 being used here, rather than 20.61. And now in the next line of the demonstration we see that 10.11 is used, and this would give the assertion as shown. Now clearly there are two apparent variables, each using the symbol alpha. However, this proposition could be written as shown without any change in its meaning. In this version, the outermost apparent variable can be more clearly seen to apply only to the consequence of the implication. Nevertheless, there is no reason why we should use two different symbols to represent the apparent variables, since, if the notation is properly understood, there can be no mistake about which apparent variable applies to what. It's possible that the symbol representing an apparent variable suddenly change in the course of a demonstration. Again, this doesn't matter, so in the demonstration of 22.94, we might see as shown. Why did the beta change to an alpha? Because it can. Using beta initially, although not absolutely necessary, this may make things a bit clearer, but then using alpha in the next line gives a visually much neater proposition. That's it. And it's always important in Principia Mathematica to be clear about which variables are apparent variables and which are real variables. And it's completely normal to have situations where there are two apparent variables which are represented using the same symbol, say x or whatever, but which have different scopes. Since we can have class symbols occurring as apparent variables, and as we see from definitions 20.07 and 20.08, this in reality is to be understood as being an apparent variable which ranges over a particular type of predicative function, which is a legitimate totality. Then we see why we need the comments on page 217. The predicative functions of a particular type will generate all of the classes of the corresponding type, and so, if classes are to appear as apparent variables, then we must assume that the classes are of the form x hat phi exclamation mark x, even though the classes may be written using alpha, beta, etc. However, since classes may be generated from non-predicative functions, then if a real variable ranges over a type of classes, then the classes may be of a more general form, x hat phi x, that is, where phi is not necessarily a predicative function. Of course, in this case, it's worth bearing in mind some of the comments that I made in my previous video concerning definition 20.01. We may have a real variable ranging over classes of the more general form, but if the variable needs to be made into an apparent variable at some point, the range of the variable must be restricted to classes generated by predicative functions. So that's it for chapter 22, so let's move on to chapter 24, the universal class, the null class, and the existence of classes. On page 93 we see that The properties of classes which are not analogous to properties of propositions are dealt with in chapter 24. The principal definitions of this chapter are shown on the screen, and I'll look at each of these definitions in turn. 24.01 defines the universal class. We can see that the universal class is defined to be the class determined by the propositional function x equals x. This propositional function is, of course, always true for objects of a given type. Therefore, the universal class has as its members all of the objects of a particular type. See proposition 24.104. Since the universal class has all objects of a certain type as its members, we see in proposition 24.11 that all classes of a suitable type are included in the universal class. Moreover, there's a universal class which corresponds to each type. That is, there are an infinite number of universal classes. The symbol used to represent the universal class is therefore ambiguous as to type. In other words, the same symbol is used for the universal class of any given type. Which universal class is being considered will have to be determined from the context. Nevertheless, due to systematic ambiguity, the symbol will be assumed to adopt a meaning suitable for the type that it refers to in a given context. So even though there is not a single universal class, there is a unique universal class for any given type. And this is since any class is determined by its membership, but is also given in the proposition 24.14, which says that any class such that every x is a member must be equal to the universal class. Moreover, we see in proposition 24.102 that any propositional function which is always true determines a class which is equal to the universal class. In other words, any propositional function which is always true could be used in place of the propositional function x equals x to define the universal class. Principia Mathematica just happens to use the propositional function x equals x. We read on page 229, any other property possessed by everything would do as well as x equals x, but this is the only such property which we have hitherto studied. And the universal class is not a new class. It already existed before chapter 24, but now it's just given a name. The definition of the universal class doesn't create the universal class, it just points it out and gives it a name. Proposition 24.141 shows that any class which includes the universal class must be equal to the universal class. That is, the universal class is the largest class, so to speak, of a given type. Moreover, the universal class is included in itself, which we know anyway from proposition 22.42. Proposition 24.22 shows that the logical sum of a class and its negation is the universal class, and proposition 24.26 shows that the logical product of a class and the universal class is equal to the former class, and proposition 24.27 shows that the logical sum of a class and the universal class is equal to the universal class. 24.02 defines the null-class. The null-class is simply defined to be the negation of the universal class. Negation of a class was, of course, defined in chapter 22. The null-class is therefore the class with no members. Proposition 24.105 shows that x is not a member of the null-class is always true. And a technical point here, since a class is uniquely determined by its membership, and the null class has no members, then it may be that there is more than one null class for a given type. This is clarified in proposition 24.15, which says x is not a member of the class alpha for every x is equivalent to alpha is equal to the null class. As with the universal class, the notation used to represent the null class is ambiguous as to type, and there is a null class corresponding to each different type. Again, that means that there's an infinite number of null classes, but only one null class for each type. Which null class is under consideration must be determined from the context. On page 31 we see there is a universal class and a null class proper to each type of object. Since the null class is the negation of the null class, then we see from 22.38 that the null class is a member of CLS, and so must be of the same type as the universal class of which it is the negation, which was defined in chapter 20. We also see from proposition 24.12 that the null class of a given type is always included in any other class of the same type as the null class. We see from proposition 24.103 that any propositional function which is never true determines a class which is equal to the null class. We also see from proposition 24.13 that any class included in the null class must be equal to the null class. Thus, the null class is, in a way, the smallest class of a particular type. And, of course, this would imply that the null class is included in itself. Proposition 24.21 shows that the logical product of a class and its negation is equal to the null class. 24.23 that the logical product of a class and the null class is equal to the null class. And 24.24 that the logical sum of a class and the null class is the former class. 24.03 defines what it means for a class to exist, and definition 24.03 says that a class exists when there is an object X such that X is a member of the class. That is, a class exists in the sense of definition 24.03 when it contains at least one member, which is confirmed on page 30 of the introduction. A class is said to exist when it has at least one member. We mustn't understand the word exist in the sense of definition 24.03 as being synonymous with the word existence, as it may be loosely understood to express being something. That is, the word exists as applied to classes in the sense of definition 24.03 is simply a word that is being used to express a particular property of some classes, but other classes may not have that property. The property being expressed is that of having at least one element. Therefore, the null class does not exist in the sense of definition 24.03 since the null class doesn't have any members, but the null class exists in the sense that it is something. It has being. There is a thing which is indeed a class called the null class. So roughly speaking, the null class exists in the broader sense, but not in the narrower sense of definition 24.03. Proposition 24.53 confirms that the null class does not exist in this narrower sense, and we also see in proposition 24.51 any class which does not exist in the sense of definition 24.03 is equal to the null class. On page 30 we see alpha is the null class is equivalent to alpha does not exist. And on page 239 we read, many of the properties of the existence of classes follow from the fact that to say a class exists is equivalent to saying that the class is not equal to the null class. This is proved in proposition 24.54. In the case of a class that exists in the sense of definition 24.03 and thus has at least one member, then the type of the class is one order above the type of its members, since we have seen that any class can always be generated by a predicative function. Recall that a predicative function is a matrix, and a matrix is always one order greater than the order of the type over which its variables range. However, in the case of the null class, we cannot say that the type of the null class is one order above that of its members, since it has no members. However, we see on page 229, the type of lambda, the null class, is determined by that of the terms x concerning which x is a member of lambda is false, whatever x may be. X is a member of lambda will not represent a true proposition, but unless x is of the appropriate type, x is a member of lambda will be meaningless, not false. Thus lambda is of the type next above that of an x concerning which x is a member of lambda is significant and false. So let's have a look at some of the propositions from this chapter, and again I'll just pick out some of the more interesting propositions. Many of them are fairly mundane and self-explanatory, but the propositions from this chapter are mostly demonstrating the particular properties of the two classes, the universal class and the null class, which of course general classes will not have. As with chapter 22, it can be informally seen in many cases that these propositions hold simply by considering suitable Venn diagrams. Again, that's not to suggest that Venn diagrams can replace a demonstration of the proposition, but they can give a nice way of visualizing what's going on here, as they do with modern set theory. So we have a very interesting proposition in this section, which is proposition 24.1. And this proposition says that the universal class is not equal to the null class. Therefore, we can either immediately or eventually deduce from this that there are at least two classes, and this is proposition 24.1. The universal class must contain at least one element, since if it contains no elements, then it would be equal to the null class. This second point, of course, applies to classes of individuals. Therefore, there is at least one individual, but we can't say whether there is more than one individual. And finally, the universal class exists, and this is proposition 24.52. On page 230 we read, "Our primitive propositions do not require the existence of more than one individual. In this case, there will be at least two classes. What would the situation be if no individual existed? I don't know, but that's not the assumption in Principia Mathematica. Moreover, we have proposition 24.52, which says that the universal class exists, that is, the universal class has at least one member. And it may be felt that proposition 24.1 is sufficient to deduce that the universal class contains at least one element, and hence that there is at least one individual. But this is not quite the case, though. 24.1 shows that the universal class is not equal to the null class, but the uniqueness of the null class has not yet been established. Therefore, it may be more appropriate initially to speak of a null class rather than the null class, until uniqueness has been established. To show that the universal class has at least one member, it needs to be shown that the universal class exists in the sense of definition 24.03. And some of these points are confirmed more formally in other propositions in this section. Most of the propositions from 24.3 to 24.495 are fairly mundane, though I don't intend by that to mean that they're not important. But I'll just pick out a couple or a few of the propositions from this chapter which, for one reason or another, I happen to like. So proposition 24.37 says that if the logical product of two classes is equal to the null class, then this is equivalent to the proposition that x is an alpha and y is a beta, formally implies that x is not equal to y. And the demonstration of this proposition makes a very clever use of proposition 13.191. 24.411 gives a way of considering a given class as a logical sum of two classes which have no common members. Many of the propositions may seem a bit unusual from time to time. Not unusual in the sense that they don't seem to make sense, but why this particular proposition has been demonstrated and maybe some other proposition for some reason hasn't been proved. And this probably usually comes down to the fact that the propositions which are proved are used in demonstrations later in Principia Mathematica. If a proposition which can be proved hasn't been proved, this probably means that it's not used at any point. And it can be fun sometimes to try to come up with propositions which aren't in Principia Mathematica and try to prove them in the style of Principia Mathematica, or maybe it's just me that finds that fun. Well, anyway, we have 24.63 which says that the null class not a member of a class of classes kappa is equivalent to, for all classes alpha a member of kappa, then alpha exists. Since kappa is a class of classes, then it can only have as members classes of a single type. Therefore, if there is a member which is the null class, then this is the unique null class which corresponds to that type. If, however, we exclude the null class from being a member of kappa, then any other class that is a member of kappa must be of the same type as the null class that we've excluded, but cannot be equal to it, since a class is completely determined by its membership. Therefore, any other class that is a member of kappa must have at least one member, and so exists. This is not to suggest that every class of a given type which is not the null class must be in kappa in general, but the implication on the right hand side of the equivalence will be true whether or not alpha is a member of kappa. So that's enough of chapter 24. Chapters 23 and 25 are concerning relations, and since they proceed precisely as in chapters 22 and 24, there's nothing further concerning these chapters for me to add here. So that brings us to the end of this video. Congratulations for surviving yet another video on Principia Mathematica, and of course we also come to the end of section C. The next section looks at converse functions, domains, converse domains, and all sorts of other exciting things. And if there's anything that you would like to ask about what I've covered in this video or any of my other videos, then please feel free to get in touch. Please remember to subscribe and hit the like button to show your support for this channel. Thank you for watching, and I'll see you in the next video.